Most people imagine nuclear war as a single moment, a blinding flash, a shock wave racing through a city, buildings collapsing, everything ending in seconds. It feels final, like a line has been drawn and nothing exists beyond it. But that picture, as terrifying as it is incomplete, because in reality, a nuclear war does not end with the explosion. In many ways, that is only the beginning. The true danger is not just what the bomb destroys in an instant, but what it sets into motion across the entire planet long after the blast fades. When a nuclear weapon detonates over a city, the immediate effects are overwhelming. A burst of intense light, hotter than the surface of the sun, ignites everything it touches. A powerful shock wave follows, crushing structures and throwing debris through the air. Radiation spreads silently, affecting those who survive the initial seconds. These are the images people remember, the ones shown in documentaries and simulations, and they are real. But they are also only the first layer of the story. What often gets overlooked is what happens next. Not minutes later, but hours, days, and weeks after the explosion. Because a nuclear detonation over a modern city does not just destroy buildings, it turns the entire urban environment into fuel. Think about what a city is made of. Countless homes filled with furniture, plastics, fabrics, electronics, cars packed with fuel, factories, warehouses, power stations, pipelines. All of it becomes flammable under extreme heat. Instead of isolated fires, what emerges is something far more dangerous, a massive, self-sustaining inferno. And now imagine that this is not just one city. In a large-scale nuclear conflict, multiple cities could be hit within a short period of time, each one igniting into a vast sea of fire. These fires do not behave like normal fires. They grow, merge, and feed on the environment, pulling in oxygen and generating immense heat. The scale is so large that the fire begins to create its own weather. Winds rush inward to feed the flames, intensifying the burn, spreading it further, making it nearly impossible to control or escape. At this point, something critical begins to happen, something that transforms a local disaster into a global one. These enormous fires start producing vast amounts of smoke and soot, not just the gray smoke from a typical fire, but thick, dark particles from burning modern materials, oil, plastics, chemicals. This smoke does not simply drift away at low altitude. The heat from the fires is so intense that it pushes the smoke upward, higher and higher into the atmosphere. This is where the nature of the disaster begins to change. Up to this point, everything we have described is still tied to the location of the explosions. But once the smoke rises high enough, it is no longer confined to the city where it was created. It enters layers of the atmosphere where winds can carry it across continents, even around the entire planet. The event is no longer local. It becomes global. And here's the part that almost no one thinks about. The real threat of nuclear war is not just how many people die in the initial blasts. It is how the entire system that supports life on Earth begins to shift. Because the planet is not just a collection of isolated places. It is a connected system where energy from the sun drives climate, where climate supports agriculture, and where agriculture feeds billions of people. Disrupt one part of that system at a large enough scale, and the consequences ripple outward. So when we ask what happens after a nuclear war, we are not just asking about survivors in ruined cities. We are asking what happens to the sky, to the sunlight, to the temperature of the earth, and ultimately to the food that sustains human life. The explosion is only the trigger. What follows is a chain reaction that unfolds slowly, almost invisibly at first, but with consequences far greater than the blast itself. In fact, the most disturbing possibility is this: many people might survive the initial explosions. They might be far away, in regions untouched by the immediate destruction. They might think they are safe, but safety in a nuclear war is not determined by distance alone, because what rises into the atmosphere does not respect borders. What changes in the climate does not stay confined to one region, and what happens to food supply affects everyone. This is why some scientists have argued that in a full-scale nuclear conflict, the majority of deaths might not come from the bombs themselves. They would come later, from the collapse of the systems that keep people alive, from cold, from darkness, and most of all, from hunger. And that idea forces us to rethink what nuclear war really means. It is not just a weapon of destruction. It is a mechanism that can alter the conditions of life on Earth itself. If the explosion is only the beginning, then the next phase is where the true scale of destruction starts to reveal itself. Because a nuclear weapon does not simply destroy a city, it transforms it into something far more dangerous. A massive, uncontrollable fire. And when this happens not once, but across many cities at the same time, the result is not just destruction. It is the birth of firestorms on a scale most people can barely imagine. To understand this, you have to stop thinking of a city as concrete and steel and start thinking of it as fuel. Every building contains materials that can burn: wood, plastics, insulation, furniture, fuel lines, electrical systems, vehicles, industrial chemicals. Under normal conditions, fires in cities are limited, contained, fought against, but a nuclear explosion changes the conditions completely. The initial flash of thermal radiation can ignite fires over a wide area almost instantly, setting thousands of points ablaze at the same time. These individual fires do not remain separate for long. As they grow, they begin to merge, feeding into each other, forming a single, expanding inferno. The heat generated becomes so intense that it starts to change the behavior of the air itself. Hot air rises rapidly, creating a powerful upward current. This rising air pulls in cooler air from the surrounding areas at high speed, effectively creating strong winds that rush toward the center of the fire. But these winds do not help extinguish the flames. They feed them. This is what defines a firestorm. It is not just a large fire. It is a self-sustaining system. The fire creates wind, and the wind strengthens the fire. Oxygen is continuously drawn in, allowing the flames to burn hotter and spread faster. Temperatures can rise to levels that melt metal, shatter glass, and ignite materials that would not normally burn easily. People caught within such an environment are not just exposed to heat, but to a violent, chaotic system that is actively pulling air, debris, and flames inward. Historical examples give us a glimpse of how devastating firestorms can be, even without nuclear weapons. During World War II, cities like Hamburg and Dresden experienced massive firestorms caused by conventional bombing. Entire neighborhoods were consumed, and the fires burned so intensely that they created hurricane-like winds. But nuclear weapons take this to an entirely different level. Instead of hundreds of bombs creating scattered fires, A single nuclear detonation can ignite a vast urban area simultaneously. Now imagine multiple nuclear detonations across different cities within a short time frame, each one creating its own firestorm, each one feeding massive columns of heat and smoke into the sky. The scale becomes difficult to grasp. It is no longer a single disaster, but a network of infernos, all burning at once, all producing enormous amounts of energy and combustion products. And what is burning matters just as much as how much is burning. Modern cities are filled with synthetic materials, plastics, fuels, and chemicals that produce thick, dark smoke when they burn. This smoke is not light or easily dispersed. It is dense, rich in soot, and capable of absorbing sunlight. The more complete the combustion, the more energy is released. But in these chaotic conditions, much of the burning is incomplete, producing even more soot and particulate matter. As the fires intensify, they begin to generate towering columns of hot air, known as pyroconvective plumes. These plumes can rise kilometers into the atmosphere, carrying with them massive quantities of smoke and debris. The hotter the fire, the stronger the updraft, and the higher the smoke is lifted. This is not just smoke drifting sideways with the wind. It is smoke being launched upward with incredible force. At this stage, the disaster is beginning to transition from something local to something planetary. Because once enough smoke is lifted high into the atmosphere, it no longer behaves like normal pollution. It does not simply settle back down quickly. Instead, it can remain suspended, spread over vast distances, and begin to interact with the Earth's energy balance. But before we even reach that point, there is a crucial realization to make. The devastation of a nuclear war is not limited to the areas directly hit by the bombs. The firestorms themselves multiply the impact. They turn cities into engines of destruction, not just consuming what exists on the ground, but injecting massive amounts of heat and particles into the atmosphere. So when people imagine nuclear war as a series of explosions, they are missing the second phase entirely. The explosions may last seconds, but the fires they create can burn for hours, even days, growing, merging, and intensifying. And with each passing hour, they are building something far more dangerous than the initial blast. They are creating the conditions for a global environmental shift, because what rises from these firestorms does not stay above the cities where it was born. It continues upward, carried by heat, driven by physics, and destined to spread far beyond the battlefield. And once it reaches high enough, it begins to change something much larger than any single city. It begins to change the sky itself. What makes nuclear firestorms truly dangerous is not just the destruction on the ground, but what they send into the sky, because the smoke rising from these fires does not behave like ordinary smoke. Under normal conditions, when something burns, the smoke drifts upward for a short distance, spreads out, and is eventually washed away by rain or dispersed by winds. It is temporary, local, and limited in its impact. But the fires created after nuclear detonations are not normal. And the atmosphere they interact with does not respond in a normal way. The key difference lies in the intensity of the heat. In a firestorm, temperatures can become so extreme that the rising air forms a powerful vertical column, almost like a chimney on a planetary scale. This upward motion is driven by basic physics. Hot air is less dense than cold air, so it rises But when the heat source is large enough, the rising motion becomes extremely strong, pulling vast quantities of smoke, ash, and soot upward along with it. This is not a gentle drift. It is a rapid, forceful ascent. These rising columns, sometimes referred to as pyroconvective plumes, can punch through the lower layers of the atmosphere. Normally, most weather happens in the troposphere, the lowest layer, where clouds form and rain occurs. Smoke that stays within this layer is often short-lived because rain can wash particles out of the air. But in the case of massive firestorms, the upward force can carry smoke beyond this region into higher and more stable layers of the atmosphere. And this changes everything, because once smoke reaches these higher altitudes, it is no longer easily removed. There is little to no rainfall to bring it back down. The particles can remain suspended for long periods of time, spreading horizontally over vast distances. Winds at these altitudes can transport the smoke across continents and oceans, gradually forming a global layer rather than isolated plumes. Another critical factor is what the smoke is made of. When entire cities burn, especially modern ones filled with plastics, fuels, and industrial materials, the result is a large amount of black carbon, commonly known as soot. These particles are particularly effective at absorbing sunlight. Instead of reflecting light, they trap it, heating the surrounding air while preventing that energy from reaching the surface below. As sunlight is absorbed by the soot layer, it warms the air at high altitudes, which can actually stabilize the atmosphere further. This creates a kind of feedback loop. The warm layer above acts like a lid, preventing vertical mixing that might otherwise disperse or dilute the smoke. So instead of breaking apart, the layer remains intact, persistent, and widespread. Over time, as more firestorms contribute more smoke, this layer can thicken and expand. What began as separate columns above burning cities becomes a continuous veil encircling large portions of the planet. At this point, the disaster is no longer tied to individual locations. It has become a global atmospheric phenomenon. From the ground, the changes might first appear subtle. The sky may look dimmer, the sunlight slightly weaker, the colors less vivid. But as the concentration of particles increases, the effect becomes more pronounced. Less sunlight reaches the surface. Days become darker, and the energy that normally warms the earth begins to diminish. This is the moment where the consequences begin to extend far beyond the original sites of destruction. Because sunlight is not just about visibility. It is the primary source of energy for the Earth's climate system. It drives weather patterns, controls temperatures, and powers photosynthesis, the process that allows plants to grow. Reduce that input significantly, and the entire system begins to shift. What is especially unsettling is how invisible this transition can feel at first. There is no single moment where everything suddenly changes. No clear boundary between normal conditions and crisis. Instead, it unfolds gradually, almost quietly. The fires burn, the smoke rises. The particles spread, and the sky slowly transforms. And by the time the full effect becomes obvious, the process is already well underway. The smoke is already high above, beyond easy reach, beyond any realistic attempt to remove it. It is circulating, accumulating, and beginning to interfere with one of the most fundamental relationships on Earth, the flow of energy from the sun to the surface. This is how a series of fires on the ground can begin to alter the sky itself, not through a single dramatic event, but through a chain of physical processes that amplify each other. Heat drives smoke upward. Smoke absorbs sunlight. The atmosphere stabilizes. The particles persist. And the result is a growing barrier between the Earth and its primary source of energy. Once that barrier becomes strong enough, the next phase begins. Because when sunlight is reduced on a global scale, the planet does not simply become darker. It begins to cool. And that shift from light to darkness, from warmth to cold, is where the true consequences of nuclear winter start to unfold. Once enough smoke has risen high into the atmosphere and spread across large regions of the planet, something subtle but profound begins to happen. It is not an explosion, not a shock wave, not a sudden event you can clearly see or hear. It is quieter than that, slower, almost easy to ignore at first. But it is far more dangerous, because this is the moment when sunlight, the most fundamental source of energy for life on Earth, begins to fade. Under normal conditions, sunlight travels through the atmosphere and reaches the surface with relatively little obstruction. It warms the land, heats the oceans, drives weather systems, and powers photosynthesis in plants. This constant flow of energy is what keeps the planet in balance. But when a thick layer of smoke and soot forms high above the Earth, that balance begins to break. The particles suspended in the atmosphere start to intercept the incoming sunlight before it can reach the ground. At first, the change might seem minor. The sky could appear slightly hazy, the sunlight a bit dimmer, the shadows less sharp. But as more soot accumulates and spreads, the effect intensifies. A significant portion of sunlight is either absorbed or scattered back into space. Less energy reaches the surface. Days no longer feel as bright. The difference is not just visual, it is physical. This reduction in sunlight has a cascading effect, because sunlight is not just light, it is energy. When less energy reaches the surface, the ground begins to lose heat. The oceans, which normally absorb and store vast amounts of solar energy, start receiving less input. Over time, this leads to a measurable drop in temperature. But unlike a typical seasonal change, this cooling is not part of a natural cycle. It is abrupt, global, and driven by an artificial disruption. At the same time, something counterintuitive is happening above. The soot particles that block sunlight are also absorbing it. This causes the upper layers of the atmosphere, where the smoke is concentrated, to warm up. So while the surface cools, the air above becomes warmer. This creates a temperature inversion, a situation where warmer air sits above cooler air, suppressing vertical mixing. Normally, air circulates, rising and falling, helping to distribute heat and disperse particles. But with this inversion in place, the atmosphere becomes more stable, trapping the soot layer in place. This is what makes the effect persistent. The very particles that block sunlight also help keep themselves suspended. The system reinforces itself. The smoke does not quickly dissipate. It lingers, continues to block light, and prolongs the cooling below. What might have been a temporary disturbance becomes a sustained shift in the planet's energy balance. From the perspective of someone on the ground, the changes would become increasingly noticeable over time. Days might begin to feel colder than expected. Seasonal patterns could start to behave strangely. Regions that normally rely on consistent sunlight might experience prolonged dim conditions. It would not feel like a single catastrophic event. but rather a steady degradation of normal environmental conditions, and this is where the danger deepens. Because life on Earth, especially human civilization, is built around predictable patterns of sunlight and temperature. Agriculture depends on growing seasons, on the timing of warmth and light. Ecosystems depend on stable energy input from the sun. Even small disruptions can have significant consequences. But this is not a small disruption. It is a large-scale reduction in the energy driving the entire system. Another important point is that this effect does not stay confined to the regions where the smoke originated. Once in the upper atmosphere, the particles can spread across the globe. This means that even areas far removed from any nuclear detonation could experience reduced sunlight. The sky above them may look normal at first glance, but the energy reaching the ground is no longer the same. This creates a disconnect between cause and effect. People living thousands of kilometers away from any conflict might not see destruction around them. Their cities might remain intact. Their infrastructure might still function. But something invisible is changing above them. The sun, still shining as brightly as ever, is no longer delivering the same amount of energy to the surface. And this is what makes the situation so deceptive. There is no obvious line marking the start of this new reality. No single moment where the sun suddenly disappears. Instead, it is a gradual dimming, a slow withdrawal of energy that the planet depends on. By the time the full impact is felt, the process is already deeply underway. This reduction in sunlight is the turning point. It marks the transition from immediate destruction to long-term environmental collapse. Because once the energy input from the sun drops significantly, the next phase becomes inevitable. The planet begins to cool, not just locally, but globally. And as temperatures fall, the systems that sustain life begin to fail, starting with one of the most essential of all, the ability to grow food. Once sunlight is significantly reduced, the Earth does not simply become dimmer. It begins to lose heat. And unlike the gentle shifts we experience between seasons, this change is not gradual or predictable. It is abrupt, uneven, and driven by a disruption that the natural system was never designed to handle. The energy that normally arrives from the sun is what keeps the planet's temperature within a narrow range suitable for life. When that energy drops, even by a relatively small percentage, the consequences begin to cascade through the entire climate system. At first, the cooling might seem modest, a few degrees lower than normal, slightly colder days, slightly longer nights that feel harsher than expected. But the Earth's climate is highly sensitive to energy balance. Small changes at the global scale translate into large disruptions locally. Regions that rely on stable temperatures for agriculture or ecosystems can be pushed beyond their limits. Crops that require a certain range of warmth may fail to develop properly. Frost can appear earlier in the season or linger longer than it should. As the cooling continues, the structure of the seasons themselves begins to break down. Under normal conditions, the cycle of spring, summer, autumn, and winter is driven by predictable changes in sunlight and temperature. These cycles determine when plants grow, when animals reproduce, and when human societies plant and harvest food. But with reduced sunlight and a colder baseline temperature, these patterns become distorted. Summers may no longer be warm enough to support full crop growth. Winters may arrive sooner and last longer. The transitions between seasons may become irregular and unreliable. This is where the impact becomes more than just uncomfortable weather. It becomes a systemic disruption. because agriculture is not flexible in the way people often assume. Crops are adapted to specific climate windows. They need a certain number of warm days, a certain amount of sunlight, and a predictable timeline to mature. If that window shortens or shifts unpredictably, yields drop. If temperatures fall too low during critical growth periods, entire harvests can be lost. In many parts of the world, especially in regions already close to the limits of viable agriculture, even a slight cooling can have severe consequences. A reduction in temperature during the growing season can mean the difference between a successful harvest and a complete failure. And because modern agriculture operates on tight schedules and large scales, these failures are not isolated. They can affect entire regions simultaneously. Another layer of complexity comes from how different parts of the earth respond to cooling. Land tends to cool faster than ocean, and higher latitudes are more sensitive to temperature changes than regions near the equator. This uneven cooling can disrupt atmospheric circulation patterns, altering winds, rainfall, and storm behavior. Areas that once had reliable rainfall might experience drought. Others might face unexpected cold and wet conditions. The stability that agriculture depends on begins to unravel. At the same time, snow and ice can start to play a larger role. As temperatures drop, snow cover may expand into regions where it was previously rare or seasonal. Snow reflects sunlight back into space, which means less energy is absorbed by the surface. This creates a feedback loop. More cooling leads to more snow, and more snow leads to further cooling. While this process might not turn the Earth into a frozen planet, it can intensify the overall drop in temperature and prolong the disruption. For people on the ground, the experience would feel confusing and unsettling. Weather would no longer behave as expected. Traditional knowledge about planting seasons might no longer apply. Farmers could plant at the usual time and still see crops fail because the warmth never arrives in full. Or a sudden cold snap could destroy fields just before harvest. These are not rare anomalies. They become part of a new, unstable pattern. And perhaps the most dangerous aspect is how quickly this shift can outpace human adaptation. Modern civilization is built on the assumption of relatively stable climate conditions. Infrastructure, supply chain, and food production systems are all optimized for the current environment. When that environment changes rapidly, there is little time to adjust. Seeds, farming methods, distribution networks, all of these are designed for predictability, not chaos. This is the stage where the consequences of reduced sunlight begin to move from environmental change to human crisis. The cooling itself does not directly kill millions of people, but it sets the stage for something that can, because when seasons break down and agriculture becomes unreliable, the next link in the chain begins to tighten. Food production starts to decline, not just in one place, but across multiple regions at once. And when that happens, the problem is no longer about temperature or climate alone. It becomes about survival, because a colder planet is not just a different planet. It is a planet where the systems that feed billions of people are beginning to fail at the same time. As the climate cools and seasons become unstable, the consequences begin to concentrate on something far more immediate than temperature itself: food. Because for human civilization, climate is not an abstract concept. It is the foundation of agriculture. And agriculture is the foundation of survival. When that foundation starts to crack, the effects spread faster than almost anything else. At first, the signs may appear as reduced yields. Crops that once grew reliably begin to underperform. Fields produce less grain than expected. Plants struggle to reach full maturity because the growing season is shorter. The sunlight weaker and the temperature lower. Farmers might try to adapt, planting earlier or choosing different varieties, but the problem is not just timing. It is that the underlying conditions are no longer suitable. In some regions, harvests begin to fail entirely. A sudden cold snap during a critical growth stage can wipe out entire fields. Frost appearing at the wrong time can destroy crops just before they are ready to be harvested. And because these changes are happening across large areas simultaneously, it is not just one country or one region experiencing trouble. Multiple bread baskets of the world can be affected at the same time. This is where the problem begins to escalate rapidly. Under normal circumstances, if one region has a bad harvest, food can be imported from elsewhere. Global trade acts as a buffer, redistributing supply to where it is needed. But in a nuclear winter scenario, that buffer starts to fail because the disruption is not local, it is global. If major agricultural regions are all producing less food at the same time, there is no surplus to redistribute. At the same time, demand does not decrease. Billions of people still need to eat every day. Governments may attempt to manage the situation by releasing stored reserves, but those reserves are limited. Modern food systems are not designed to support long-term shortages on a global scale. They rely on continuous production, constant movement, and stable conditions. When production drops and uncertainty rises, the entire system becomes strained. Another critical factor is how interconnected modern food systems are. It is not just about crops in the field. It is about fertilizers, fuel, transportation, storage, processing, and distribution. A disruption in climate affects all of these at once. Lower temperatures can reduce the efficiency of farming. Energy systems may be under stress. Transportation networks can become unreliable. Even if some food is produced, getting it to where it is needed becomes more difficult. Livestock production is also affected. Animals depend on feed, which comes from crops. If crop yields fall, feed becomes scarce. This leads to reductions in meat, dairy, and other animal products. In some cases, livestock may be culled because there is not enough food to sustain them. This further reduces the overall availability of calories in the system. As supply decreases and uncertainty grows, prices begin to rise. Food becomes more expensive, and for many people, less accessible. This is where the crisis shifts from a production problem to a humanitarian one. Wealthier regions may be able to secure limited supplies for a time, but poorer regions are hit much harder and much faster. Hunger begins to spread, not because food has disappeared entirely, but because it is no longer available to everyone. Social and political consequences quickly follow. Governments may impose export bans to protect their own populations, further reducing global availability. Panic buying, hoarding, and black markets can emerge. Tensions rise both within and between countries. The stability of societies, already under stress from environmental changes, begins to erode. What makes this stage particularly dangerous is that it unfolds over time. It is not a single catastrophic event, but a cascading failure. Each harvest that underperforms makes the next one more critical. Each disruption in supply chains reduces resilience. Each increase in price pushes more people toward the edge. And unlike a sudden disaster, this kind of crisis does not end quickly. It can persist, deepen, and expand. For individuals, the experience becomes increasingly personal. It is no longer about distant fires or changes in the sky. It is about empty shelves, smaller meals, and the growing uncertainty of whether there will be enough tomorrow. The abstract idea of climate disruption becomes a daily reality. And this is where the original assumption about nuclear war begins to collapse completely. The idea that survival depends on distance from the blast is no longer true. Someone thousands of kilometers away from any explosion can still be drawn into the consequences. Because once food systems begin to fail, the effects reach everyone. This is the point where the chain reaction, started by explosions and firestorms, reveals its most devastating outcome. Not immediate destruction, but the slow breakdown of the systems that sustain human life. And as food becomes scarce and hunger spreads, the final and most unsettling realization emerges. The greatest threat of nuclear war may not be the bombs themselves, but the global famine that follows. By the time the effects of nuclear winter fully unfold, the nature of the disaster has completely changed. What began as a series of explosions and firestorms has transformed into something far more pervasive and far more difficult to escape. The destruction is no longer defined by geography or proximity to a blast. It is defined by the slow, relentless breakdown of the systems that keep people alive. And in that new reality, survival is no longer about where you were when the bombs fell, but whether the world can still produce enough food to sustain you. In the early days after a nuclear conflict, there would still be a sense of separation between those directly affected and those who are not. Entire cities may be gone, while others remain physically untouched. For a moment, it might seem as if distance offers protection. But as the weeks pass and the atmosphere continues to block sunlight, as temperatures fall and harvests begin to fail, that illusion starts to disappear, because hunger does not respect distance. It spreads through systems, not landscapes. At first, the signs would be subtle: food prices rising, certain items becoming harder to find, governments beginning to ration supplies. These are signals that something deeper is wrong. Not a temporary disruption, but a sustained imbalance between how much food is needed and how much can be produced. And once that imbalance grows large enough, it becomes impossible to hide. As shortages intensify, daily life begins to change. Meals become smaller. Variety disappears. Staple foods, the basic grains that billions depend on, become scarce. For many people, especially in vulnerable regions, this shift happens quickly. What was once a stable supply becomes uncertain, then unreliable, then unavailable. And unlike other crises, there is no easy substitution. Food is not optional. There is no alternative system waiting in reserve. What makes this situation uniquely devastating is that it affects everyone at once. In most disasters, aid can come from outside. Resources can be moved from unaffected areas to those in need. But in a global food crisis caused by nuclear winter, there are no unaffected areas. Every region is under pressure. Every country is trying to secure what little remains. Cooperation becomes more difficult as survival instincts take over. As hunger spreads, the effects go beyond physical weakness. Societies begin to strain under the pressure. Systems that once maintained order, distribution networks, markets, institutions start to falter. When people cannot access food, stability erodes. Desperation leads to unrest, and unrest makes it even harder to manage what resources remain. The crisis feeds on itself, growing not just through scarcity, but through the breakdown of coordination and trust. For individuals, the experience becomes deeply personal and unavoidable. It is no longer about abstract concepts like climate or atmosphere. It is about the daily reality of not having enough to eat. The body begins to weaken. Energy fades. The ability to work, to think clearly, to function, all begin to decline. And this happens not in isolation, but across entire populations at the same time. One of the most unsettling aspects of this scenario is how it reframes the idea of survival. In most depictions of nuclear war, survival is about avoiding the blast, finding shelter, escaping immediate danger. But in this case, survival depends on something far less visible and far more fragile: the continuity of global food production. You could be thousands of kilometers away from any explosion, with intact infrastructure and no direct damage, and still face the same ultimate threat as those closer to the conflict. This leads to a stark realization. The deadliest phase of a nuclear war may not occur in the first minutes or even the first days. It may unfold slowly, over months, as food systems collapse and hunger spreads across the planet. The timeline stretches, but the outcome becomes no less severe. In fact, it may be more so because it affects a much larger portion of humanity. And this is why the idea that people might not die from the bomb, but from hunger, is not an exaggeration. It is a logical conclusion of the chain reaction that begins with nuclear detonations and ends with the disruption of the Earth's ability to sustain life as it normally does. The bombs ignite the fires. The fires fill the sky with smoke. The smoke blocks the sunlight. The cooling disrupts agriculture. And the failure of agriculture leads to famine. In the end, the most terrifying aspect of nuclear war is not just its immediate violence, but its ability to turn the planet itself into a hostile environment for human life, not through sudden destruction alone, but through the quiet removal of the conditions we depend on every day: light, warmth, and food. When those begin to disappear, survival becomes uncertain for everyone, regardless of where they stand when the first explosion occurs.